equals 2e to the x. Very good. I agree. Plus 3. Very good. Plus 15x squared. Perfect. So I have the derivative. And now, so it said one more time, it said, show that this curve has no tangent line with slope 2. What do I have to do next? Exactly. Very good. Perfect. Okay, so what does this mean? We're asked to show that this function does not have a tangent with a slope 2. In other words, the derivative is never 2. So if I move 2 to the other side and try to solve this equation, so 3 minus 2, I'm going to write 1 already, plus 15x squared equals 0. What will be the idea in case, if it's true? If it's true that this function does not have a tangent with a slope 2, in other words, its derivative is never 2, what am I expecting to get? Right. So in other words, that this equation has no solutions, or at least not real solutions. Okay, good. We could think in terms of the intermediate value theorem and see, but that may be a little bit iffy. It will take some time because I can check the entire real line to see if this function is ever 0 or not. The other possibility is put it in the graphing calculator or put it in Maple. So if we go to the graphing calculator and we put it in y equals, and I have 2e to the x, 2 e to the, oops, I didn't mean that, 2 second e to the x, and then plus 1, and then plus 15x squared, and 15x squared. And I will analyze this and double check. And here's another way, even an easier way. What type of number, what type of number is this? Definitely greater or equal to 0. It could be 0 if x is 0, right? What type of number is this? Obviously, strictly greater than 0. What type of number is this? Yes, definitely greater than 0. So the only possibility for this to be 0 is when x is 0, maybe. So this will be 0, but this will never be 0. So again, I can look at the graph, but is this ever going to be 0? Since this is a positive number, and only this can be 0, nothing else can be 0. So even if this is 0, then I'm adding a positive quantity. Is 0 plus a positive quantity ever going to be 0? No. So I can already conclude from just this simple analysis that this will never be 0. Also, if you look at the graph of the function, you will see I worked on with my pre-calculus class on something else here. So let's say if we want to look at the standard viewing window, this is what we had in y equals 2 e to the x plus 1 plus 15x squared. So when you look at the graph, it's expected everything way above the x-axis. So what we conclude about this function then, what do I have to write? I have to write a conclusion. Something has to be written for this as the answer. What do I write? That y, no, that y does not have a tangent with slope, very good, slope 2. Is this okay? Good, very good question. Nobody could see what I was writing. Sorry about that. So y does not have a tangent with slope 2. Very good. That is the easiest thing to see. Or you graph the function. Yes, 31. On 182. Let's look at 31 on 182. 31. Z equals A divided by y to the 10th and plus b e to the y. We're asked to differentiate. Let's look at the question. The question is asking us to differentiate the function. Perfect. Very good pick. So what do I do here? I look at this function, and first of all, I'm asking myself, I see 3 letters in there. I see A, I see B, I see Y. What is going on? Y is the variable, indeed. Y is the variable. So maybe it would have been nice for them to write this, or ask us to find dz over dy, and that would have been very clear. But of course, A and B, as we know, are normally reserved for constants, parameters, constants, not variables. Good, perfect. So what I recommend here is changing this before you start differentiating into what? What is the other option for this fraction? Excellent. Very good. So plus b e to y. That's a good choice. So then z prime of y would be negative 10a y. Very good. Plus b e to y, because ey prime is e to y. Good. Now you can rearrange it and can write negative 10a divided by y to the 11th, if that's what you want to do. I recommend that. Plus b e to y. Perfect. Very good pick. Anything else? Yes, Tony?
I don't know if we've gotten to this one yet, but in section 3.2,
yes,
page 190, number 45.
So 45 on page 190. Let's take a look. 45. Yes, we did have a similar problem. We can work on this one. So 45 says, if f of x equals e to the x times g of x, where g of 0 is 2 and g prime of 0 is 5, find f prime of 0. We can work on this one, yes. So let's copy it. So we are given that f of x equals e to the x times g of x. And we are told, again, f of, is it f? No, g, I'm sorry. So g of 0 is 2, g prime of 0 is 5, and the question is asking us to find f prime of 0. Perfect. Perfect. Good pick. What do I do? Any suggestions? Ian? Careful, careful. If, yes, Tony?
I was, Dave, you can say what you mean.
Okay, here's what yes, Thomas?
Oh, so you practically, you can use the definition to differentiate the x.
You are talking about not a definition, because I don't have G, but you're talking about the product rule. Good. So what I was going to say, but on wonderful suggestions, what I was going to say is this. If I come to you and say, find f prime of 0 for me, what would you say to me first? Tony?
You need to find f prime of whatever.
You have to ask me for the function, right? You can't plug in something if you don't have the function, right? You don't have what to plug it in. So, of course, I have to find f of f prime. I cannot determine f prime of 0 before I have the f prime of x. Excellent. So then, right? Thomas is right. I have to find f prime of x. How do I do it? Let me remind you the rule. And I recommend mine, but you can use the one in the book. I prefer this, but you decide. 1 prime times 2 plus 1 times 2 prime. The book, remember, reverses this for whatever reason. It's the same thing. It's correct. 1 prime times 2 plus 2 prime times 1 is the same thing. Now you tell me what you want to do. So we are differentiating e to the x times g of x. Yes, Tony?
I think I did it the book way, but
That's fine.
you would end up getting e to the x times g prime to the x.
Careful.
Well, I didn't plug g of it.
Times g of x plus. You still have to keep it in this order. You can reverse the order in the product, but please still keep the order. 1 prime 2 plus 1 times 2 prime, or 1 prime 2 plus 2 prime times 1. So it's okay because it's a sum, but if you do that for a ratio, that would be a catastrophe. So be very careful with that. So the book, you're right. The book puts the derivative as a second no matter what. That's fine. But be very careful here. Be very careful here because, see, you can reverse these two if that's what you want to do. But here, if you do, then the whole thing collapses. Okay, I'm in agreement with that. So you're saying that then you put this as the second. You said G, D. Okay, that's fine too.
Okay.
I prefer this order because it's always 1, 2, 1, 2, 1, 2, 1, 2, and I don't have to twist anything in my head. But I guess it's a matter of habit.
That was actually my question for the problem, was I did it the book's way and got the
That's
right
fine.
answer, but I wasn't sure if we were allowed.
You are allowed to use a method from the book, of course. So as I said, it's e to the x prime times g of x plus e to the x times g prime of x. And now I do have something that represents f prime. I don't have everything, but I do have something that represents f prime, and now I can plug in 0 in it. That's okay. So f prime of 0 will be e to 0, which is 1, g of 0 plus e to 0 again, which is 1, so plus g prime of 0. And all this information is given to me. I have g of 0, which is 2, and I have g prime of 0, which is 5, so the answer is 7. Is that okay? Perfect. Yes, Ian?
So the product rule is f prime times g plus g prime times f. Here, f of x is equal to e to the x times g of x. So isn't that like that's that like, so we'll do e to the x times g of x prime times g of whatever g is.
Let me write it, so make sure that we talk about the same thing. So let me write what you are saying.
So what I'm thinking is
So you want to write that f prime of x equals, dictate, and then we'll analyze it.
is e to the x times g of x. No, so like e to the x, so see how f of x is equal to e.
So you want to put this first and this second? So you want to write this? Addition is commutative, so I can put this in here and I can put this in here because they're added.
Not that.
Okay, let's try it again.
So f of x is equal to
You're talking about f prime, or you want to go back here?
yeah.
Okay.
F of x is equal to ex e to the x times g of x.
Okay, so I have that.
So then we're finding the product is f prime is equal to f prime of x plus.
It's right here. This is the product rule.
Yeah. So I'm supposed to enter that for f and then g is 0, so times g prime.
You have to give me what you're saying so I can write it.
So okay, so
F prime of x equals?
if f prime of x is equal to f of x, so e to the x times g of x. So f of x is equal to e to the x times g of x, right?
Okay.
If you take away the dot, that's what it's going to confuse.
Okay. So you don't like the dot. I'm taking away the dot. Sorry about that. Good. It's gone.
Okay, so then g of x would be g of,
So you want plus, you want minus, so
now I want a dot,
now you want a dot. Okay.
times g of x, with g prime of x, sorry.
Okay.
And then plus
Yes.
f prime.
Again.
Yeah.
F prime.
No.
I think I
I'm
understand.
saying it wrong, but
I think I understand the confusion. Okay, I think I understand the confusion. So let's look at this function like this. What is it composed of? It's composed of a function, which I'm going to call 1, and it's composed of another function that I'm going to call 2, and they are multiplied. So e to the x is the first function, g to the x is the second function. Forget about this notation for a moment, okay? Let's just look at the product of these two functions. And when I differentiate the product, I have to have, if you're using my rule, e to the x prime multiplied by g of x, e to the x prime multiplied by g of x. I'm here with plus e to the x multiplied by the second function prime. This is one way of expressing the product rule. You can have three functions like the ones you gave me here.
so then
This is f, and this is f prime as well.
what's that?
Right here, this is f, what I covered it. This is your f. Your f prime is this.
Like the f consists of two functions.
That are multiplied.
Okay.
Is that better?
Yeah.
So you understand that's what I said. Forget about this notation for a moment. Just look at what f of x is equal to. So because this is definitely a product of two functions, I have to use the product rule. If you wanted the one in the book, or if you want the one that I present, 1, 2, 1, 2, doesn't matter. The answer will be the same. So this is your first function prime multiplied by the second function plus the first function multiplied by the second function prime. And this, if you want now to write it, this is f prime of x. And then all we had to do was to replace x by 0, and we got g of 0 plus g prime of 0. Those numbers were given to us. I had to replace them, and I got 7. Is this better? Perfect. Okay. Very good. Good questions. Tony, anything else? Anyone? Anything else?
I got one more.
Yes. Yes.
3.1, so that's page 189, number
Yes.
29.
So 29 on 189?
Yes.
Perfect. 189, 29. I see it. So it's f of x equals x to 5/2 multiplied by e to the x. Maybe we should take 1 minute and work on this. And then we'll do it together. 1 minute. Because it's exactly the same idea with the previous function. So let's find f prime. Let's read what we're asked to do. The same thing, differentiate. Yes, Thomas? Did I copy something else?
I think you copied.
Of course, I always do that. I did. I can never get away with anything in this class. I did copy 28 by mistake. I'm sorry. So I have f of x. You took Ben's place. Ben was doing that to me all the time in the previous class. Thank you, Ben. Did you pay Thomas? Okay, good. So we are trying to find the derivative of this function. Perfect. Now, again, I recommend this, but it's up to you. I accept anything that works and is legitimate, of course. Okay, so I differentiate this. Again, 1, 2, 1, 2. So 1 prime times 2 minus 1 times 2 prime divided by 2 squared. It's up to you what you want to do. I recommend that. But again, it's a matter of habit. So once you get into a habit, use it. I'm fine. Good. So the top function is x squared. The bottom function is 1 plus 2x. What do I do?
X squared, I mean, x 2x.
Yes, I differentiate the top. So this is this prime. Excellent. 2x. Now I have to copy the bottom with parentheses. 1 plus 2x. I got to minus now. I have to copy the top. Very good. And now I have to differentiate the denominator. 2 indeed. And the denominator now, 1 plus 2x, everything squared. Now be very careful because I've seen it before. How much credit should I give to a student who simplifies 1 plus 2x with 1 plus 2x from the bottom? 0 credit. Excellent. Thank you. I appreciate that. So then I will have to do what next?
Then you have to
Correct. So 2x plus 4x squared minus 2x squared over 1 plus 2x, everything squared. And then I already distributed. Now I have to combine like terms. So 4x squared minus 2x squared is 2x squared plus 2x divided by 1 plus 2x squared. I saw in some of your work, you are expanding the denominator. Please don't. There is no need. You're wasting your time. We want the denominator to be as is, factored. And I highly recommend factor out 2x and get x plus 1, and you will see in the next chapter why. So bear with me. This should be the final answer. Tony, is this better?
Yeah, I didn't factor out 2x, I just ended up factoring out 2, and then I think the back.
I don't know how the answer is presented in the back, but this is preparation for the next chapter.
That's understandable. Thank you.
Right. At this point, if you leave it like this, you'll get full credit, but I recommend always, if it's a negative leading coefficient, always factor out -1, and always keep the numerator factored if it's factorable, and never expand the denominator. There is no need for that. Okay. Other questions for me? Yes. Yes? I heard 55, but I didn't hear the page. Or you said 3.1?
Yeah.
Okay, that's fine. I don't need the page then. 55. Find equations. Very good. It's a good question. Find equations of both lines that are tangent to the curve y equals 1 plus x cubed and parallel to the line blah blah blah. One more time. Find equations of both lines, apparently there are two, that are tangent to the curve y equals 1 plus x cubed and at the same time parallel to the line 12x minus y equals 1. So I need to copy. So this is page 182. So y, again, was 1 plus x cubed. I have to copy correctly, as I can't get away with anything in this class. Okay, just kidding, just kidding. Good. So we want tangent, equations of tangent lines parallel to the given line. So let's say, I think we talked about something similar last time, maybe I'm wrong. But let's say this is the function. Well, it's not really, it should be something like more like this. But anyway, so let's say we have a tangent, we have a line that I'm just drawing the idea. I haven't looked at function. Obviously, it will have a positive slope, so this may be the line. And then we're asked to find the equations of two tangents. Apparently, there are two. There are parallel to the line, and they are to the given line, and they are tangent to the graph of x cubed plus 1. So this is the idea. So what do I need to do? How do I think about it, and what would be the first step? Any suggestions? Okay, I'll find the derivative. Very good. So then y prime equals, very good. Perfect. Then find the slope of,
line.
exactly. I have to find the slope of the line. How do I find the slope of a line? Exactly. I have to present it into mx plus b. So then I will solve for y, in other words. So negative y equals negative 12x and plus 1. And then I divide both sides, or multiply both sides. In this case, it's the same thing, by, very good, by negative 1. So y equals 12x minus 1. What is the slope then? The slope of the line, 12. The slope of the line is 12. What do I do next then?
Set the equal to 12, the derivative.
Exactly. So I have to set 3x squared equal to 12. And what type of equation is this? So I know how to solve it. Very good. Quadratic. How do I continue?
Divide both sides by 3.
By 3. Very good. I get x squared equals 4. And now
Square
take the square root. Since it's quadratic, how many solutions I expect?
2.
Okay, perfect. So then x equals, indeed, plus or minus 2. We are asked, one more time, it says, find equations of both lines that are tangent to the curve, blah, 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 and parallel to blah, blah, blah.
So basically, you plug the two back into the
Exactly, because I need to find these points. I'm going to call this P and I'm going to call this Q. I know that this has x coordinate negative 2. I know that this one has x coordinate 2. But I don't know the y coordinate. Good. And again, already Thomas told us what to do. He said plug it back in. So I have negative 8 plus 1 or 8 plus 1.
so it's
Negative 7. And the other option is 9. So we do have 2 points. P negative 2 comma negative 7, and we have Q 2 comma 9. Let's do one of them so we can move on, and you'll do the other one. So we have the slope, which is 12, and let's just fill it in. So we have, yes, how do I write, and what am I writing? Yes? Yeah, so let's write, first of all, the point, yes, point slope 4. So this is negative 2, this is negative 7, and this is 12. Can you take it from here so we can continue? Yes? Perfect. Other questions from me? And of course, you have to do the same thing with the other point. Other questions from me? Is there anything else? Okay, real quick, see if you had any questions from last Monday. This was a question from our test. Then we looked at the handout that I gave you, and if you remember, I said every class I would like to spend 3 minutes on anything you would like to discuss in 3 minutes from the previous chapter. So I'm looking for my handout. I got it. So here's the handout. So I would like to spend every class, if you remember, I said every class we will review one topic from the previous test. So you tell me from these 6 pages, this is what we covered in chapter 2, all this. So tell me one topic that you want to talk about for 3 minutes. Any of this. Last time we talked about this very important theorem that allows us to swap the operators. This is a crucial thing that I need in this chapter. when we differentiate a function raised to a function which we have no rule for other than what I'm going to show you. So the swapping up of the operators is allowed and possible under very important strict restrictions of continuity, etc., etc. So we talked about that. So is there any particular topic? I would like you to always have one topic in mind from chapter 2 that we can discuss in a couple of minutes and refresh our memory every time. Oh, this is what I didn't give you. You're not here. Sorry about that. So give me a topic for 2 minutes, 3 minutes, or less. Anyone? Anyone? If not, I will choose one to refresh your memory on.
Limits at infinity.
Okay, very good. So we want to talk about limits at infinity. Excellent topic. Here it is. It's on page 5 of this handout. At the top, limits at infinity. So when x approaches infinity, very good topic. When x approaches infinity or when x approaches negative infinity, similar. If the function that we determine the limit for, if we get a number, if the limit exists, in other words, if it's a number, what do we conclude about y being that number? It's what? So if we determine the limit of f of x when x approaches infinity, and the result is 5, what do we conclude? Exactly. Y equals 5 is a horizontal asymptote. Okay, very good. Now, what if we determine the limit as x approaches infinity from, for example, 1 over x squared? So limit as x approaches infinity or negative infinity of 1 over x squared. What is that going to equal to? Right, so it will be 0, and in this case, the horizontal asymptote will be y equals 0. Very good. That's another thing here. We learned how to draw a graph of a function given different conditions. What conditions were we given?
X is less than 0.
Something happens, exactly. Or if as x approaches 2 from one side, the function approaches infinity or negative infinity. So all these conditions, what did we do with them? We graphed an example of a function. That was not a unique answer, right? Well, you could come up with a function, I can come up with a different function. But all those conditions are fulfilled. We remember those examples? Okay. We learned how to find a vertical and horizontal asymptotes and the corresponding limits. So if you're asked on a function to find all vertical and horizontal asymptotes, just saying x equals 2 is a vertical asymptote is not good enough. You have to show the limits or calculate the limits left and right of 2. Just saying this function has a horizontal asymptote y equals 5 is not good enough. You have to prove it with limits. Not all functions have the same horizontal asymptote on both sides. They may have one horizontal asymptote on one side and another on the other, or just on one side and not the other. So you have to be careful. We practice finding limits for all kinds of functions, and we have that handout that I gave you with 3 pages of limits. And I'm still updating that handout. Every time I find something new, I put it in there that I didn't before. Good, very good. It was a quick review, very good. So coming back to what we covered last time, let's browse through and you'll say stop if you have any questions. So we looked at the product and quotient. We proved the quotient differentiation of a ratio. So we proved the whole thing from the beginning till the end. So hopefully we will never forget that, and we will never differentiate f over g as f prime over g prime, correct? Because there is a specific rule for that. Good. Okay, then what else? We looked at and we used the definition on x cubed. We wanted to make sure that it was correct, 3x squared. So we did that. We use the differentiation rules on the square root of x. We use differentiation rules on 1 over x. These are crucial rules that I need for the entire semester. And then we practice with different examples. And we differentiated ratios. And we also proved we used maple on this one. The limit of a to the h minus 1 divided by h was nothing. When h approaches 0 was natural log a. And we know now what e represents. What does e represent? I don't know if I wrote it here. I think I left it on the handout. Yes, I wrote it on the handout. That was e to the h minus 1 over h. And the limit of h approaches 0, what was it? 1. Okay. Then we looked at a situation in which we were asked to determine the tangent and the normal line to a particular point on a curve. And I think that this was pretty much, yes, this was another example that we did together, similar to what you asked today. And I think that was pretty much it. I said, please bring the maple on Monday. I'm extending it till Monday. That's fine. And then we started, that's exactly where we left it off, right? I'm looking for my handout. Just gave it to Eric. Okay, here it is. I have another one. So that's exactly where we stopped. We analyzed this function, and that is on the last page. It's on the last page of our handout for last time. This one. Okay. We did not get the chance, I don't think. We did not get the chance to graph it. We only showed that it was continuous. I'm going to use this result now. We showed that it was continuous at -1, and we showed that it was continuous at 1, correct? And that's where we stopped. Would you agree? We showed the definition of continuity at a point, and we said it has to have a unique tangent, and it appeared that it did not have a unique tangent at -1. At 1. Okay? So based on this, I would like to finalize this problem. So one more time, this is the handout from last time, 3.1 and 3.2. And we are on page 5, the bottom. And I would like to quickly go through something else from here, whatever we decide to do. And I would like to graph the function and its derivative. That's what we did not get the chance to do, correct? Ready? So let's finish this up. So in order to graph this function, how do we start? What is the first step? We know it's continuous everywhere. At least that we've established, and we'll talk about differentiability in a minute. So tell me, how do I graph this function? What do I have to do? What do I have to find first? Absolutely, the domain. So can anyone give us in interval notation this inequality in interval notation? Very good. What about the middle one? With a bracket. Good. And what about the last one? I completely agree. So therefore, now looking at this, I'm going to use those symbols under numbers, as you know, but I would like to identify the domain first. What would you agree or say about this? So what is the domain? Correct. Very good. Everything. Nothing is missing. What key numbers I have to have in my chart? Right. I have to have -1. I have to have 1. And I will also put 0. Look at the symbols under -1, the interval. open to the left and close to the right. And what about under 1? Yes, close to the left and open to the right. And those two symbols, if you are using my method, they have to touch, because there is nothing I can put in between. So now which function? I know it's an overkill, but I would like to have it right there. These don't have to be in order. So that's why I need to make sure that I'm using the correct piece on the correct interval. So which function I use for negative infinity to negative 1? I agree. Which function I use for the middle? I agree, and x. Perfect. Okay, so then on the left-hand side, what type of function is it? How many points I need? It's a polynomial, but furthermore, linear. How many points I need for a linear function? 2. Okay, very good. So to the left-hand side of negative 1, let's say negative 2. Plug it in. So it's negative 2 times negative 2 is 4. 4 plus 1 is 5. Now let's plug in negative 1. 3 indeed. Am I allowed to plug in negative 1 in this? Because this is an open parenthesis. It's an open interval. Am I allowed to plug in negative 1? The answer is no. But if I don't plug in negative 1, I have to plug in negative 1.000000000, blah, blah, blah. So I know that this will be an open point, depending on what number I get here, though. Okay, so let's plug in negative 1 in x squared. What do I get? 1. Plug in 0. It's quadratic. I know how to graph it, right? So 0, and then 1. I agree. What about on the other side? 1 and 2. Very good. Any questions? I'm looking at, for just 1 second, I thought I don't remember for a second, did we show at negative 1? Oh, I copied the function incorrectly. Because I remember from last time the function was continuous, and look what I'm getting. I'm getting 3 on one side and 1 on the other. So forgive me. I didn't, right? Last time we showed that it was continuous everywhere, right? So obviously when I said, ooh, 3 and 1, not possible. Right here, negative 1. Sorry about that. So I have to make the correction. So when we plug in, say, yes, of course. Thank you. Thank you. Thank you. So with the negative 2, we have 4 minus 1. And with negative 1, we have 2 minus 1, which is 1. Right? We showed last time that the function was continuous everywhere. I couldn't have 3 and 1 here. Right. So the function is indeed continuous. So I would like the graphs of the function and the derivative to be one under the other. I'm not sure whether you have enough room here or not, but I'm not going to use that because I need more room. I know that for sure. But you can use that, of course. So this will be for G, and this will be for G prime. Very good. So from left to right, add negative 2 is 3. Add negative 1 is 1. This should be an open point, but since these two are the same, I will go back and fill it in. So on the left-hand side, this is a line, linear function with a negative slope, which is negative 2. Then in the middle, this is quadratic. And then another linear function, 1, 1, 2, 2. Very good. Next step, I would like to determine the derivative, and then I'll come back and graph it. So can anyone give us g prime for x less than -1, for -1 less than x less than 1. Notice that I have not used the equal symbol yet, and for x greater than 1. Can anyone give us the derivative on the interval -∞ and -1? Very good, -2. Can anyone give us the derivative on -1 to 1? X. Good. And on 1 to infinity? Very good. Although we did show last time one thing. What did we show about the derivative? Okay, here it is. That's how we finished. That's where we finished. And we said it has to have a unique tangent, right? So we looked at what happens at -1. And the left-hand side, the slope was -2. And the right-hand side, the slope was -2 at that point. But it didn't happen at 1. The slope on the left was 2, and the slope on the right was 1. What did we conclude? That the derivative will have a what at 1? A jump, indeed. Indeed. Very good. So let's go back. So between -∞ and -1, here's my -1, right here. The slope is -2. I'm going to write it like this for a moment, although we know the answer. So that's the graph of the first derivative, or the derivative of this function, between -∞ and -1. Now, at -1 is -2. So I'm ready to fill it in. I have to graph 2x, which is a straight line, between -1 and 1. So at 1, the function is 2, with an open point. At 0 is 0, that's another point, and here's our graph. Here's our derivative. However, between 1 and infinity, here's the graph of the derivative. What do we conclude about g? One more time. I know we already said it last time, but what is our conclusion now? The function g is or is not continuous everywhere? Is continuous everywhere. Is the function g differentiable everywhere? Where is function g not differentiable? At 1. Very good. So I will go back and make my adjustment. I have to put back in the -1, but I cannot put back in 1. I cannot do that because the function has a jump there. The derivative. So say it again. I cannot. So g prime, very good question. G prime does not exist at 1 because the function is not differentiable at 1. Good question. Good. Any questions for me? Okay, moving on. Now, find the values of m and b. Let's read what else I have on this handout, and then we decide. Because I would like to, let me see how far I am with the video. Okay, I'm